Here's a wild thought. By the end of this video, you will have programmed a real quantum computer. Not a simulation, not a toy. An actual quantum processor sitting in a lab running your code. And you don't need a physics degree to do it. My name is Olivia, and I'm going to show you how. This is a 4-part course called Use a Quantum Computer Today. It will take you from no prior experience in quantum computing to hands-on programming a real quantum computer without assuming any background besides basic curiosity. In Lesson 1, this video, we'll build and run our first quantum program together. Lesson 2 covers quantum basics, where we'll dig into the underlying principles that govern quantum computation, plus just enough math to make it all click. Lesson 3 will cover a more sophisticated quantum circuit tied to real-world applications. Lesson 4 is the big picture. We're going to tackle the biggest misconceptions about quantum computing and discuss where the field is actually headed and what we're trying to achieve. So first things first, how do we run a quantum program? The first thing you're going to need is an IBM Quantum account. I already have one because I work here, and I use the computers regularly. But setting up one is very straightforward. Head to the IBM Quantum Platform, enter your information, and you'll receive 2 things. First is 10 free minutes of Qiskit runtime, which is actually pretty substantial. It's more processing time than you might think. And second is an API token. Save this somewhere safe, and don't share it with anybody, because this links to your personal account. Now we'll go ahead and get coding. I'm going to open a Google Colab notebook for a quick and easy Python environment. You can absolutely install Python and Qiskit locally on your own machine, and I recommend doing that if you decide, hey, this quantum stuff is pretty cool, I want to keep going. The installation guide is linked here. But for now, we'll use Google Colab and install our basic packages, Qiskit Air and Qiskit Runtime. Before we write any quantum code, we need to set up our environment. First, I'm installing the core Qiskit packages we'll need. This includes visualization tools so we can actually see our results, the IBM Runtime so we can run on real quantum hardware, and Air, which lets us run our circuits on a simulator instead if we so choose. Next, I'm importing the key components we'll use throughout this lesson. The quantum circuit class is how we'll actually build our quantum programs. It's where we define qubits and apply operations. Then I'm bringing in plot histogram, which we'll use to visualize measurement results. This is how we interpret what our quantum circuit did when we ran it. The preset pass manager helps optimize our circuits so they can run efficiently on real hardware. This becomes really important as circuits get more complex. More on this later. And finally, I'm importing tools from the IBM Runtime, including the sampler, a primitive that lets us execute circuits and collect results, and the Qiskit Runtime service, which connects us to IBM's quantum systems in the cloud. So at this point, we've got everything set up to build, simulate, and eventually run our first quantum program on a real machine. Now, before we actually write code, let me show you what we're about to build using the IBM Quantum Composer. On the platform, navigate to the Composer, click on Help, and then build your first circuit. You can follow the tutorial here. This circuit walks you through the hello world of quantum computing. But what did we actually do? Well, we used 2 quantum gates, this H gate and this weird circle with an X through it. What do these instructions actually mean? The H gate is called the Hadamard gate, and it's one of the most important tools in quantum computing. It takes a qubit in a definite classical state, a 0 or a 1, and puts it into a superposition, which is our first quantum buzzword. We'll look at what that means mathematically in Lesson 2. But for now, think of the Hadamard as a command for the qubit to become an equally weighted superposition of 0 and 1. Without the math, it's a little tricky to describe precisely, but I think for now it's fair to say that you can imagine that this is a qubit that is a little bit of 1 and a little bit of 0 simultaneously. Next, we implemented a C0 gate, which flips the second qubit whenever the first qubit is in the 1 state. This combination creates something called a Bell state. Bell states are famous in quantum physics. A Bell state is a special kind of entangled state involving two qubits. And that's our second quantum term, entanglement. In essence, quantum entanglement means that the qubits are so strongly correlated that you can't describe one independently of the other. Even if the qubits are physically really far apart, measuring one instantaneously determines the state of the other. So now, our two qubits are correlated in a way that has no classical equivalent. It's pretty remarkable that you can create something this special with just two gates. The outcomes of this specific Bell state are either 0, 0 or 1, 1, as you can see here, meaning that every time the first qubit is measured to be in 0, the second qubit will also be measured to be in 0, and vice versa, unless some noise or an error has occurred. Next, let's do a quick environment check. Think of this as the seatbelt step. We confirm versions, confirm imports, and make sure circuit drawing works in this runtime. And if anything fails here, it's usually a dependency issue, and fixing it now prevents confusing errors later. But this all looks good. These are the latest versions of everything we need. Let's proceed. I start by creating an instance of the quantum circuit class with two qubits. First, I apply a Hadamard gate to the first qubit. This puts it into a superposition, so instead of being 0 or 1, it's now a little bit of both at the same time. Then I apply a CNOT gate, using the first qubit as the control and the second as the target. This is where the magic happens. This operation entangles the two qubits together. Now their states are no longer independent. Measuring one instantly tells you something about the other. After that, I measure both qubits, which stores the results in a classical register. And finally, I'm going to draw the circuit so we can actually see what we built and visually check it. At this point, we've created our Bell state, specifically the phi plus state, which is one of the simplest and most important examples of quantum entanglement. Next, we're going to define a helper function that handles running a quantum circuit and retrieving the measurement results. It takes in three things: the circuit we want to run, the specific backend or device, and the number of shots, which is how many times we repeat the experiment. Inside the function, the first step is optimization. I use a preset pass manager to transpile the circuit for the specific backend. This step rewrites the circuit into a form that the hardware actually understands, while also trying to make it efficient. The result is what's known as an ISA circuit, basically a version of our program tailored to the specific machine we're running on. Next, I initialize the sampler, which is the tool we use to execute circuits and collect measurement data. Then I submit the job, running the circuit multiple times based on the number of shots we specified. Once the job finishes, I retrieve the results and extract the measurement counts. And what we get back is a dictionary that tells us how often each outcome occurred across all shots. This is the core output of most quantum programs. Now we need to connect to a real quantum computer through the cloud. First, you'll notice a line where I save my IBM Quantum API token. This is what authenticates me and gives me access to the quantum hardware in the cloud. You only need to do this once, and you should always remember to keep your token private. After that, I initialize the Qiskit runtime service, which is our gateway to the IBM Quantum systems. Once connected, I can start selecting a backend, that is, the actual quantum device I'm going to use. Here, I'm choosing the least busy available system that meets certain criteria, like being a real device, not a simulator, and having at least 127 qubits. This helps reduce queue time so we can get results faster. Alternatively, I could directly specify a particular machine if I wanted to target a specific processor. It's thinking. And finally, I print out the name of the backend we'll be using so we know exactly which quantum computer is about to run our circuit. Next, I pass that circuit into the helper function we wrote earlier, along with the backend we selected. I'm running it on 1,000 shots, or 1,000 times, so we can get a good statistical picture of the results. You technically don't need to specify this here because I already set that as a default in the argument of the helper function, but I just left it here to remind us. This sends the circuit off to the quantum device and executes it repeatedly. then returns the measurement counts. Why 1,000 shots? Well, IBM QPUs are inherently physical systems that can pick up on noise, and measurements can occasionally be wrong. Device calibration drifts over time. Running on hardware also introduces practical considerations. Jobs can sit in a queue because so many people might be using the device at the same time. That's why I chose the least busy backend. You'll also need to make sure you choose a shot count that balances clear statistics with time and cost constraints. And remember that if cost and time are constraints, you can still just run your job to practice on one of the simulators because that doesn't use any of your free runtime allocation. Finally, I plot those results as a histogram. And this is where things get really interesting. Instead of seeing all possible outcomes, you should only see 0, 0, and 1, 1, roughly in equal proportions. That's the signature of entanglement. There are some small occurrences of 0, 1 or 1, 0 here due to noise and errors. Now, the two qubits are correlated, so even though each individual result looks random, together they follow a very specific pattern. And just like that, you've run your first entangled quantum circuit on a real quantum computer. Congratulations. Now remember, if you want to use a simulator, you could also try running this using the air simulator, and you'll get about the same histogram, but without the 0, 1 or 1, 0 noise artifacts, because the simulator is perfect. However, simulators and real quantum hardware are not equivalent. If simulators could do everything real hardware can do, why would anyone go through all the effort of building these machines? Well, simulators are useful for checking expected results on small circuits like ours, or for troubleshooting, like I mentioned. But they cannot replicate real quantum effects at scale. As you continue your quantum education, and we hope you do, remember there's no replacement for programming and practicing with real quantum computers. So congratulations on creating your first quantum circuit on a real quantum computer. That's all for lesson 1, but we're not done. In lesson 2, we're going to take a closer look at superposition, entanglement, and really understand what's happening under the hood in this circuit. And don't be scared, but we're even going to introduce a little bit of math. But it's going to be fun, I promise. At the end of every episode in this series, I'm going to be adding a learning objective so you can build upon the skills that you started when we were programming together. For this episode, I encourage you to go back to the code that we just started and figure out how to program the other 3 Bell states. Now, we're going to be using one of those other Bell states in a further episode, so this will serve you well. Good luck, and share your results in the comments below. We'll see you soon for episode 2.